All right. So, um, so before we get into the final project today, there's one thing I wanted to talk about first, and that would be kind of the last mention of what the heck we're doing with bolted joints. So we've talked about stiffness, talked about computing the stiffness of the clamp members, stiffness of the bolt, and now the question is, okay, so why the heck do we care about all of this, right? So to answer that question, let's see if we can play the game one more time. See if also see if this will fit. There we go. All right. So really the question is now, how is the load that we put on a bolt or that is applied externally, how is that distributed in the joint? We've talked about how it's distributed, how the stress is distributed. We've computed how the stiffness is distributed. Now we have to talk about how the load is distributed. So come on, see if I'm as cool as I want as I want to be. Okay, so now that we've come up with a spring rate, kind of a force per unit length of extension or contraction for both the bolt and the members, it's kind of intuitive to say that deformation then is directly related to load and stiffness. That's pretty straightforward. So I can say something like the load that's being exerted on the bolt is into the spring constant of the bolt, and that's equal to however far the bolt's being stretched. And that's going to be that same amount of how much the bolt stretch is going to be however much the members stretch. That kind of makes sense. It's one joint. It's moving as one. So that also means that whatever load is on the members, it's related to the spring constant of the members and that same deformation. We're not going to assume that they are the same because they probably aren't, right? If I have a whole bunch of rubber being held together by a steel bolt and the joint's in tension, I'm going to guess that most of the load is going to be taken up by the bolt because it's so friggin' stiff, right? Intuitively, if I have a platform supported by a whole bunch of really stiff springs and a couple of soft ones, it's the stiff ones that are going to keep it from compressing or going down when I step onto it, right? It's intuitive that strength should distribute itself proportional to the load should distribute itself proportionally to the stiffness of the members holding that load. But we need to, one, prove that, and two, apply it in some way that gives us a numeric result. So game on. Yeah. P is just the load. P is a force. P bolt, load of the bolt, members, or whatever that thing that looks like an M is the force that's acting on the gripped members. Cool. So given that both the bolt and members are experiencing the same deformation, we can just solve this puppy out. Say like the load on the bolt. Say I'm just arbitrarily picking that, and that will kind of confirm our intuition that the load on the members or on the bolt is just distributed in proportion to their stiffness. If they're both of the same stiffness, great, then they both have the same load. We get that intuitively, and the math is reflecting that, which is great. If one's stiffer than the other, the bolt's significantly stiffer than you expect, and math backs it up that it's going to hold more of the load. So let's play around with this a bit more. We also know from statics that the total force acting on the joint, call that P joint, the total load on joint has to be the summation of the load on the joint, load on the bolt rather, and the load on the members. So that so much is obvious, right? If I do a free body diagram, these are all separate members. Correct. The things that are being clamped. Yeah. So so when you look at this, when you do a free body diagram in here, the bolt and the two or more things being clamped by the bolt are separate objects. So we're not talking. So when we talk about like the load on the bolt and the load on the members, we're not talking about necessarily internal forces. These are each distinct bodies with forces acting on one another. Forces acting on one another. So he can do a summation of forces like this and say that the total load on the joint is some summation of all the forces in the joint, which includes both bolt and members together. Using the relationship that we just came up with, can kind of simplify this a bit. Put it all in terms of just the bolt load. I'm going to shorten stiffness. I'm going to start shortening the members to M and bolt to B, just a heads up. And if we if we factor out bolt, so that's PB 1 plus KM over KB. Is that the load in the joint? So that's K. Promise. Something like that. Or if you want to flip it around, the load in the bolt second as it decides which way is up again. Probably. There we go. PowerPoint, we believe in you. There we go. So we can flip this around and say that, whoops, I need to get my pen back first, that the load in the bolt is just proportional to the load in the joint by the proportion of stiff, which will by the ratio of stiffnesses between the bolt and the member. So that makes some amount of sense, right? Cool. All right. So this kind of tells us how load is going to be distributed. What I find really cool about this is that this same intuition holds so true across so many different applications. Like this same idea is how stress distributes in a fiber reinforced composite. That's why we add the glass in there, or the carbon fiber, or whatever. It's much stiffer than the glue, than the matrix material. So it ends up eating up most of the load. also makes analysis a pain in the friggin' butt. But this same idea holds true. It's super, super cool. In case you end up doing more stuff with this. So I need to erase it manually by keeping them. 1 second. Get rid of all that. There we go. All right. So once we got that, I wonder if I can find how to erase it off. The answer is yes, but it's going to take time and it'll be annoying. Cool. All right. So once we got that, that's great. But we've said before that there's one more step to this. PJ will be loading the joint, so distribute it, support into that. But we're also going to include here preload. So we've talked about this before. This is just a force that I apply to the joint that is over and above whatever load is being placed in the joint by, these are the bolts on the base of a wind turbine. So it's going to be loaded by the fact that there's wind blowing on the top of the turbine, the whole tower is trying to fall over and stuff. In addition to that kind of design load, I'm going to add a preload. So the purpose of adding preload is essentially to make sure that the joint does what I want it to. So the joint is only doing this. The load is only distributing itself because the members in the grip are clamped. If they are not clamped at any point in time, this whole magical thing goes away. Load stops being shared between the bolt and the members, and everything's held by the bolt. And that's not what we want. A bolted joint is a load sharing scheme, and we want to keep that up for as long as we can, because it means that we can actually we can sustain a force larger than the yield strength of our bolt potentially, because we're sharing the load with the members that are in the grip. But we need a preload in order to ensure that. If we don't have a preload, it means since that we're a person breathing on the bolt, more or less, I'm exaggerating, away from the members not being clamped, or if the nut comes loose, things aren't clamped anymore. So a good preload is essential. Actually, typical practice is to load the bolt with the preload to its proof strength. It's called the factor of safety is usually almost 1 with respect to the proof strength, such that that load sharing is ensured. It's a really kind of interesting deal. But that means that we should probably be concerned about stress. So let's talk about that. So if this is our gig, and say that we can come up with an appropriate preload based on a torque wrench or a force indicator, so on and so forth. Say that we know what the preload is. That means that the stress in the bolt is, that's pretty straightforward to come up with, right? We grab that. This area being the tensile strength area for the bolt that we talked about before. That's pretty straightforward. That means we can come up with like a factor of safety with respect to the proof strength. Something like that. That's pretty straightforward. But as said, like this factor of safety, that's not really what we're necessarily concerned about. Like we anticipate that that's going to be close to 1 because we want a large preload, because what we're really concerned about is the joint separate. So what we really need to figure out is some factor of safety with respect to joint separation. So we go back and we expressed, can I erase this, by the way? Cool. So we expressed a statement for the force on the bolt, right? We said the bolt is the joint's load times ratio of stiffnesses. Well, because the joint is the summation of forces in which the joint load is the summation of the bolt load plus the member load, means that we can just substitute this in and come up with the load in the members being something like this.
When we're saying we're loading it, what direction is that load?
Tension. Yeah. Good question. So for the members to separate, the load in the members would be equal to 0. So if we take this expression up here and solve for P joint, we're going to call it P and P naught. For this condition when the load in the members is 0. If we go ahead and solve for that, we could use that to come up with an expression for a factor of safety with respect to joint separation. So we'll call that something like P naught over the applied load. Or if you want to use the instrumentation that we have been using, the P naught over P joint. So if we work all that out, it is P joint when the load in the members is 0. Yeah. So if you take the equation I just erased, set it equal to 0, solve for P joint, that is P naught. Cool beans? Sweet. All right. So if you solve that out, get something like this. Some of this extraneous stuff, which directly has, I'll make this a little bit more clear here too. So the factor of safety and separation is directly proportional to the amount of preload that you throw on this. So I mean, sure, you don't want to like yield the bolt because you're putting preload on. Actually, well, depending on your application, you might want to. Some people actually load a bolt plastically with their preload because it keeps the joint clamped for longer. depends on the strength of your bolt and what it's made out of and all that jazz. When I want to do that, usually preload is just your proof strength, but it makes sure that your members stay clamped and your load sharing stays on. So there we go. Any questions with that? This is kind of the end of bolts for us. I was hoping we get to fatigue and bolts, but it looks like we have to keep going. So we can talk about gears and brakes and springs.
It seems almost counterintuitive to me because, like, you're clamping the bolts down until they're almost healed.
Yeah.
And then you're putting more tension on the joint.
Yeah.
But the bolts don't.
Right. It is right. It is right. It is weird. Absolutely. That's what I thought first. But I'm going to say this. Which called, but the important thing to remember is that when you're pulling on the joint, you're pulling on it via the clamped members. And think of it like this: you're not pulling on like a hunk of steel; you're pulling on a spring. And that spring has to deform in order to pass load on to the bolt. So it's and it's already under a whole bunch of load now. So it's gonna be harder for that member for that spring to pass on load because it has to soak it up first, and then it passes it to the bolt. So by clamping everything down and making it tight, you're adding a second spring in parallel with the spring that is the bolt. So it turns into this crazy load sharing scheme. And how well the load is shared between those is directly affected by how tightly things are. It is definitely counterintuitive. The only way that I can really think about it is by like pulling on springs. If you think of like, I'm just taking like a washer and I'm pulling on a washer, that's a bad joint. That's what's called, that's a joint that's not clamped. Because yeah, if I just pull on a washer, I'm just pulling a bolt along. I'm just applying force to the bolt. But that's not really what a proper bolted joint is. Cool beans. Any other questions? Cool. All right. So that's all we got for bolted members. Time for the fun, meaning final project. Alrighty. So this is also in Canvas right now. So, there we go. All right. Well, final project is to design this. Church call, but here's the fun part. So we've talked a lot about design of different components and such, and so on and so forth. Your task isn't just to design a screw jack. Your task is to explore the design space for a basic screw jack. So here's the design handed down to you by the powers that be, quote unquote, TM. It's the same one that you had for homework before. You have a pair of links on each one of these arms of a specified width, and so on and so forth. You have lead screw in the center. You have some load pressing down at the top. The thing that is of interest is, okay, if you have to make this for like a Toyota Echo, small stricken car in the US, Which call this could be one size. If you have to make it for a Dodge Ram 3500, this would be another size, going from like a curb weight of like 2,000 pounds to a curb weight of 7,000 pounds. Not to mention that the Toyota Echo has a ground clearance of about 4 inches, and a Dodge Ram has a ground clearance of like a foot. Let's call those jacks will look very, very different. Those two jacks will look very, very different. Question is, how will this design change as we go between those two kind of extremes? Or if you want to think of it as of the design space as having corners to it, what you call in one corner you have what you call like on your horizontal axis you have weight, vertical axis you have maximum height that you need the jack to get to. We're going to look at we're going to look at many combinations of weight and vertical reach and ask the question of what does that do to the performance of our jack? And that is your project. When you talk about per performance, you're talking about how quickly the jack will traverse under its maximum design load. So if you're designing it for a 3,000 pound max safe working load, and the vertical traverse of like 18 inches, say, how fast will it traverse that? As well as what will the weight of the jack be? Because that's kind of an important deal when you're hauling this around your car and you're going to change a tire, right? So those are the considerations. So those are the design parameters that we're looking as fallouts. In other words, those are for each jack design that you can consider. That's what we're interested in knowing. And your jack design should span all combinations of vehicle weights and vertical reaches specified here. So specifically, looking at loads from 2,000 pounds to 7,000 pounds and maximum vertical reaches. So the maximum height that the jack can achieve physically, going from 10 inches to 22 inches. A couple other things of note. This is going to be an electrically driven jack. So it will use a single 180 watt motor, weighted 2 pounds. It is most efficient at a speed of 180 RPM, or or when it has a torque of about 9.5 Newton meters. You'll need to come up with some sort of a gearbox in order to keep the motor running at that speed and transform that into whatever torque you need in order to run the bolt.
When you say designing gearbox, do you want
2 gears?
Okay.
Spur gears.
Okay.
Unless you want something harder.
Well, you want 2 gears to achieve the gear ratio we want.
Unless you want to add more.
Okay.
Idea is make it as compact as you can, as simple as you can. So yes, it means planetary gearboxes are out, unless you really want to do that as design.
Okay. Because I think they do use planetaries for a lot of those small high reduction.
For this one, the problem with planetary gearboxes in this particular application is that they're an inline gearbox. So it changes the orientation of your thing. Unless you add another gear set to the end of, unless you add a spur gear to the end of it, so you can, instead of having the motor hanging off the end of the jack, you can put it into the center of the jack.
Okay.
So you're going to end up using a spur gear somewhere in here, and I've messed with the numbers a bit. I've given you enough of a derated motor that it more or less which call the planetary gearbox is more or less already factored into this.
Okay.
You just have to do the last mile.
Okay.
You just have to gear it to the jack. If you want to think of it that way. I am not anticipating you doing more than adding a pair of spur gears.
Okay.
You can do whatever you want. I'm not anticipating him adding more than a pair of spur gears. Again, you can do whatever you want. Make it as complex as you desire, or have it be simple. Some other things to note. Fatigue life of all parts must allow for the jack to reach its maximum vertical extent and come back at least 500 times. If it has an infinite fatigue life, great, but it has to do it at least 500 times. So you have to be checking parts for fatigue life. Also, so whatever screw that you select for this screw-driven jack, that screw must be self-locking under the load that is computed. It does give you some flexibility there to change the screw depending on what you decide is appropriate for a given load. Similarly, though, you should also be checking the design factor of safety for every jack that you could come up with, such that for all members, the factor of safety for static failures, that's, and when I say all, that's bearings, linkages, screw, gearing, everything, is at least 2.5. We're going to assume that due to how jacks are operated, all loads are pseudostatic, meaning you can neglect impulsive loads. Also, due to how jacks are usually operated, we are assuming that lateral loads, or loads that would be out of plane, meaning going into or out of this page, that those are negligible as well. So just consider loads coming from the static weight of the vehicle up here. You'll have to assume that something concerning how that load is distributed to the jack based on whatever your use case is.
Should we consider the bars as like 2 bars or 1 thick bar, or is that up to us?
It is specified in here that it is 4 sets of with 2 parallel bars each. The width of each bar being 30 millimeters.
Okay.
I had to throw something metric in. Cool. As said, your design space spans a range of vehicles from curb weight of 1 ton to 3.5 tons, and vertical reach from 10 inches to 22 inches. As said, I'm not interested in just testing like from 2,000 pounds and 10 inches to 7,000 pounds and 22 inches. I want to see, okay, if I have a light vehicle with a lot of ground clearance, what does that jack look like? If I have a heavy vehicle with a tiny amount of ground clearance, what does that jack look like? I want to span all combinations. When I say all combinations, I mean at least 25. Try to distribute them evenly, please. You can do more if you feel like it, at least 25. Now, what I'm looking for in terms of how this data looks, I mean, sure, you could do all this right up in a table and be done with it, and that's great. Like tabulated data is fantastic, but so the manufacturer wants to get an idea, wants to get an idea of what this design space looks like and what trends there are. So I want a carpet plot. A carpet plot, if you don't know what it is, looks something like this. So this is a carpet plot that I made of the what you call of the pulley system from your first test, based on varying the diameter of the shaft and the load applied to the pulley. What you call plotted on a grid of static loading factor safety here, and then ratio of the maximum reverse loading over the endurance limit on the y-axis. What I've done is I've come up with 9 different points that correspond to different loads and shaft diameters. So if I'm on the yellow line, that's a line of constant load, and then I go from one diameter to another diameter. That's 0.07 inches. That black line's 0.075 inches, and I can see trends here. So for example, I can see that factor of safety and my endurance limit ratio varies more or less linearly with load if I go along the line of constant load. But if I go along the line of constant diameter, it varies exponentially. That's the kind of stuff you can see on a carpet plot. And as someone who's going to be looking at your design to evaluate what jack I should make, that's what I want to be able to see. So I specify up here that I want to make a carpet plot with, instead of a factor of safety and my endurance limit ratio on the X and Y axes, since I've already set specifications for both those for every jack design. You can think of every point on this plot as being a separate jack design, or for the exact scenario that I've done here, it's a different shaft design. Instead of factor of safety and this endurance limit ratio on the X and Y axis, I like traverse speed and overall jack weight on the X and Y axes, kind of my performance parameters. And then instead of lines of constant shaft diameter and constant pulley load, I want lines of constant working load. So that's whatever vehicle weight that you're designing this for, and lines of constant vertical reach. So how high the jack can go, which may be limited by buckling, yielding, or just physical crap, stuff gets in the way. Well, you'll have to figure that out. All right, so that's deliverable 1. I want a carpet plot with all your designs on it. 2, I do want a tabulated design in summary. Seeing trends is one thing, knowing a little bit more about the designs is another. So this would be for all 25 designs, and it would include traverse speed, jack weight, safe working load, maximum vertical reach, static factor of safety, and its endurance life. I would call the endurance life would be really nice to know, and how many times the jack can be actuated. So the units of endurance life are 500 lifts or 1,000 lifts, something like that. If it's infinite, great. The specification was it just has to be more than 500 times up and down. Cool. I do want to see an example of your computations for one design that includes computations of all parameters from fatigue, buckling, yield, self-locking, torque required to rotate the screw, all of that. Also, you will likely have to make additional assumptions for your design outside of those specified here, be it in terms of how much load the jack is actually taking up when it's lifting a 1-ton vehicle. Is it taking up the entire ton? It's taking up 3/4 of the ton, half ton, whatever. just I'll anticipate that you will justify them. If justify whatever assumptions or design choices that you make if they're not included in this in this document. If there is a assumption or design choice that appears questionable, ask me about it. If it's something that invalidates the assignment, the answer is probably no. Looking at you, Edward. But there are a large number of reasonable assumptions that you can make to work within this problem and get the data that you need. Are there any questions? Cool. All right. So that's your project. It is due at the time of your final exam. Your next question is what the heck? Why do we still have a final exam? Answer is this project does not cover everything that we'll cover in the class because it seems dumb to make a project you can't do until the week before finals. So this does not necessarily cover everything that we'll be doing in class. As a result, your final exam will be more like a small test that will just cover the last few weeks of class. Yes. Yeah, that was called. It should be. You need to check. I need to check my calendar, but it'll be in the next few weeks. It'll be before November. Put it that way. Any other questions? Yes.
Does this look right? It doesn't look right to me.
MSRP versus horsepower?
Yeah.
I mean,
this is just test data. I was thinking
right.
HTSP could make carpet plots.
Oh, okay.
But that carpet plot does not look right.
So my carpet plot has the example of being 1, clean, and 2, based on non-arbitrary data. MSRP, very arbitrary.
Okay.
It does have some trends to it, as you can see on that plot, but the trends can fall apart. Okay. So a carpet plot does not have to look like this in order to be correct per se. What you have is a valid data set and your plotting parameters against it. A carpet plot is supposed to show trends. When those trends fall apart, the carpet plot says, well, bud, your trends are falling apart. All right, so there's nothing else.